my recording was paused. I'm just turning it back on now. So, you know, if anyone wants a recording of this, we could go later. So we've identified a start and we've identified the end time. We're going to use these two to figure out the average rate of change or the average speed, which is what question 1 is asking us to do. So let's go ahead and apply big idea number 5. We're going to draw a line between these 2 points. That's what big idea number 5 says. And big idea number 5 also says that the slope of this line is going to be the speed. That's what it tells us. So then let's go ahead and find the slope of this line. In order to find the slope, let's label our points. Ignore the second 0, 0, but let's make this x1, y1, because that's how we find slope formula. So x1, y1, and it's in your big ideas packet. And then we get x2, y2. And then again, if you look back, the only reason I'm not going back is because I drew on my screen, but if you look back at big idea number 5, the formula is y2 minus y1 all over x2 minus x1. So it's written there for you. I'm going to write it right here. So this is the formula for finding the slope. And once we find the slope, that's going to give us the speed, or the average speed that the teachers were going at. So let's go ahead and calculate this. And again, make sure that you yourself you can either type up this work, you can write it out, and then just put it on your own mini final as we're doing this. So we have y2 is down here, it's 4.185. Minus, and then we're going to subtract y1, which is simply just 0, all divided by, then we have x2, which is 9, minus, and then x1, which is just 0. So then what we end up with is 4.185 divided by 9, because minus 0 kind of does nothing. So before we do this calculation, I do want to remind everyone that, remember, D was distance in miles, T was time in minutes. That's what the original prompt told us. So that means if I'm doing change in Y over change in X, what we're finding out is the units are going to be miles per minute. It's miles on top, minute at the bottom. So I just want to make sure we're keeping track of our units. And then let me know what y'all get. 4.185 divided by 9. You can use your phone to calculate what we get. Yeah, so I have a good question while everyone else is figuring that out. Could you find any point on the line and just find the slope? No, we actually had to specifically choose. We had to choose these 2 points, which are the correct points. We couldn't just choose any points for number 1. The reason why we chose 0, 0 is because the teachers start when t equals 0 minutes and a distance of 0 miles. That's what that first 0, 0 represents. Now, the second point we got was because in the problem, they said that they were driving for 9 minutes, or the officer said they were traveling for 9 minutes. And so that's why we went up here to choose our second point at 9 minutes, and then we clicked on the graph and we got this output as 4.185. So this wasn't just any 2 points. We had to actually look back at the prompt and figure out what are the 2 points that we need. So that's a very good question. All right, let me know what anyone gets here. So 4.185 divided by 9. Let's try to simplify what we get as our speed. Once someone has an answer, go ahead and we'll see what it compares to and all that.
Wouldn't it be I got 0.465?
Okay, 0.465. I believe I get that same thing. Let's go ahead and write it down. Awesome. And everyone else should verify you get the same thing. So repeat it. 465?
Yeah.
Okay, I remember that number. Let's use it. I just remember the ultimate answer, but awesome, because we're not done yet. So we have remember this number represents miles per minute. Now I don't know if anyone remembers here, but remember the CHP officer was saying they were going above 75 miles per hour. So we need to kind of make sure that we convert this into miles per hour. Not we need right now what we have is miles per minute. We need to convert this to miles per hour. So how do we do that? Does anyone remember what we did? I'll pause to see. And again, you can type it, you can unmute, or if you don't remember what we did, you just ask yourself right now, okay, so if I have miles per minute, how can I change that to be equivalent to miles per hour? Any ideas here? How can we change this into mph, miles per hour? Hmm.
Don't you multiply it?
Yeah, I think so. What do we multiply it by? Does anyone know? What can we multiply this by?
60?
Awesome. And do you remember or do you know why we're multiplying by 60? It's right. I mean, yes, we're going to multiply by 60, but I wonder if we know why.
Because it's 60 minutes in an hour.
Yes, yes. Awesome. Thank you so much for sharing that. That was sincere, right? Sometimes the voices don't show your photo, but
Yeah.
perfect. So there is 60 minutes in 1 hour. So 1 hour. That is why we will multiply by 60. That is absolutely correct. Yay. And then you want to actually write that down too in your mini final. Like, okay, I got this answer for the average rate, but I need to remember multiply by 60 because, and then Cecilia just said it, there's 60 minutes in an hour. So that's why we're doing that. So make sure you make yourself a little note right now, or you can even ask us to repeat that. But the reason why this also works and converts to miles per hour is because notice how we have this set up. If y'all remember last time when we were finding what the area under a curve represented, I kept doing this process, but the fact is when you multiply, something cancels out. And what you're going to be left over with is going to be miles per hour. Now, yes, there's a little one right here, but if you divide anything by one, it's just whatever the number is. So ultimately what we're going to have is, let me go ahead and rewrite this in red. We're going to have this is equal to, and I'm going to have to write over here, 4, oops, we actually gotta, well, because we're multiplying, we gotta do 0.465 times 60. We gotta multiply that. Go ahead and multiply that. Let me know what y'all get. So 0.465 or 0.65 times 60. What do we get here as our answer?
27.9.
Yes, perfect. We get 27.9. And then it's gonna be miles per hour. Or just, you could just put mph, whatever, miles per hour. Yes, again, there's a little one here that we haven't taken care of, but if you divide anything by one, that's just, again, still going to be equivalent. Anything divided by one is just the number itself. So it's still 27.9 miles per hour. So on average, the teachers were actually going pretty slow, right? On average, but that doesn't really tell us what's happening within the 9 minutes. A lot can happen within 9 minutes. Someone could literally speed at over 100 miles per hour, but then slow down. I mean, if you look at the graph, notice how speed is changing because slopes are changing throughout the graph. So this on average, they're not speeding, of course, but we need to continue to investigate this to see if any time in their drive, if they were ever speeding. And that's when we're gonna lead into that big idea that you mentioned, Jasmine, the one about instant rate of change. So first, before I move on to that, if you feel like you're gonna forget any of this or you haven't copied it down, you should take a picture. But just make sure that you use the picture as a reference as you re-explain this on your own and your understanding. Yeah, let me know if anyone has a question though before we move on from this part. And yes, that's the answer for number one. But again, you want to make sure you justify, make connections to the big idea. Without that, you can't get proficient. You'd be at most like developing. Yes, this is for number one. That's right. This is for number one on the mini final. And yes, the recording is on Remind from yesterday. So definitely, I think I did this. I did the same process and walkthrough yesterday as well, but I'm doing it here with you all as well. New ideas are coming up, so each time this video or this recording is going to be different, of course, because yesterday's group had different approaches to this and this group's, but it should be, it's the same kind of walkthrough from yesterday as well. All right, cool. So if there's no questions, again, make sure you take your pictures. I'm going to go ahead and clear this up. So, like we said, obviously they're not speeding on average throughout their drive, but what's happening in between their drive? When we're trying to figure out what's happening, like at specific points in time in their drive, that's when we're talking about instantaneous rate. So let's go ahead and go to number two and see what they're asking. So, by the way, so we finished this, we used the 2 points. Let me go ahead and just finish off what we did. We used 0, 0. And this is just little notes that you could look at, but I'm not gonna actually type out the answer. Again, that's gonna be your thinking to do and to type out. So we use 0, 0 and 9, 4.185. And you wanna make sure that you justify why did we choose these points. Next, we found slope. Slope. Think about why will this give us speed? And again, the answer to that is on your big ideas on why the slope does give you speed. And after that, you just go ahead and put your answer, enjoy your work. Yeah, so show your calculations. So yeah, those are the tips for number one. Now let's go on to number two. So now we got to figure out, well then, so we know on average in their 9-minute drives, they were not speeding. They were going a pretty low, speed. Now we got to figure out what is the fastest speed the car actually reached during this drive. So what was the fastest speed that the car ever went? And that's why when we're looking at big ideas, I'm going to transition us into the next big idea. So we could reference big idea number 6. So that is like when, for example, we're talking about instantaneous rate of change. Well, what is that? That is when we're trying to find the rate of change at an exact point in time. And then a good example to think about this is the speedometers, right? When you're driving your car, you look there, that's your instant speed. That's your speed at that exact moment. that exact point in time. So it's not really like an average. It's more like this is my instant. This is the speed I'm going at now. It's not like we're taking 2 points and two separate points that are apart by a minute or two and then calculating. It's actually giving us the speed at that moment. So that's why we got to use this big idea to determine whether or not the teachers at any point in their drive were speeding. So I'm going to just make a little note here. The first off, big idea number 6, instant rate of change represents finding the speed at an exact point in time. And that's why we need this, because we got to figure out within their drive, did they ever speed? Another big idea we'll be using is, so there's big idea 6. If you scroll down to big idea number 7, it tells you how to actually calculate the instant rate of change. Another way to say instant rate of change, there's shorthand ways like IROC, instant rate of change, or the long way is instantaneous rate of change, but they all mean the same thing. So this is what we're going to have to do, because this is the process. We're going to have to estimate. So you can estimate and approximate the instantaneous rate of change by choosing points. So again, we're going to choose points that are, but these points have a specific thing. It says that are infinitely close to something called our point of interest. Okay, so there's 2 points. They have to be really close to something called a point of interest. Oh, and then look, we're gonna again find the slope between these 2 points. So that's the process. And then here's just if you want to further think about it. But the example I gave in class was we were trying to figure out how fast this ball was going at exactly 2 seconds. And in order to estimate the instantaneous rate of change, first off, I chose 2 points that were very far apart. But then I went ahead and I moved this second point closer and closer to that point of interest that I was interested in. And ultimately, this last answer right here, this last one right here, this would be the approximation for the instant rate of change. So we kind of don't have to do this part. These parts were just shown to show you that, hey, if I go closer, that's going to give me the best estimate for the instant rate of change. So that's going to be the process that we're going to have to do. But then we got to figure out what is the point of interest. That's another thing. Let me clear this up. And I see something in the chat. Let's see tomorrow. Okay, just making sure. Okay. So then that's what we're going to be doing. So again, I'm going to make sure I write this down. You also need big idea number 7 because it tells you exactly how to do it. The process for estimating instant rate of change. Rate of change. Okay, so those are the 2 big ideas we need. Now, I'm going to go ahead and transition us to the Desmos that we actually did in class, because we could totally borrow from that Desmos and apply it here. So, and then y'all can totally take screenshots from as I'm working on the Desmos. So I'm going to go to our class Desmos. I believe. I'm going to go to mini final. And then because we have a mix of period 6 and period 1s, I'm just going to go ahead into a random dashboard. So random class. So it looks like I went into period 3. Go ahead and anonymize this. Okay, cool. So in order to help us answer the next question, to figure out what we're trying to figure out is, well, what was the fastest speed that the teachers had went at any time in their drive? right? We haven't yet answered that. All we've answered, number one, was how fast on average were they going in 9 minutes. And an average isn't going to give us that much info. The slide that I want to talk about is this one. So go ahead and take the time to read it. The reason why I'm reviewing this with y'all is because we're going to apply what we see here to figure this out. So it says, consider the graph showing an ant moving through time. And this is going to help you to prepare to analyze the slopes in the model that you have for your mini final. So here are the two questions that you see. Between which 2 points is the speed of the ant the greatest? Between which 2 points is the slope the steepest? So those two questions actually mean the same thing. So between what 2 points is the slope the steepest? Or in other words, when was the speed of the ant the greatest? How we could kind of answer this is if you draw some lines between the 2 points and you can visually see which is steeper. So one of the most common choice was points A through B. So let me show you. If I was to draw a line, that's what it would look like. And then the slope would be pretty high because the line is going, it's very steep looking. And then we're gonna connect B through C to kind of compare that slope. See, it looks a little bit less steep. And then we connect C and D, which looks even less steep. So then if I just kind of scroll down so you could see the slopes, notice how the slope between A and B is very steep. I mean, imagine if you're walking up on a hill and you had to walk up a steep kind of hill that's like very inclined upward, it would be very hard to walk it. But then over time, it would get less steep and then less steep. So it looks like the most steepest is going to be indeed between A and B. Cool. Again, let me know if anyone has questions, but we're going to be applying the steepness of slopes into our mini final. So that's just that one. All right, let me go ahead and clear my screen. Okay, so the real important one is going to be on that group Desmos on slide 7. Look at this. So there was like a 50-50 kind of thing happening here. Let's see how this question is even different. It says, consider the graph showing an ant moving through time. Again, it's going to help you for your mini final. Now it's asking us though, at which point is the instantaneous speed of the ant the greatest? So remember, instantaneous means the ant speed at a particular exact moment in time. When is that? And then I put recall, instant rate of change is the rate of change at an exact instance or moment. So that means at an exact point. At an exact point, we have the speed the speed of the ant is the greatest. So how we can figure this out is I'm gonna again start drawing lines. But this time I'm gonna just draw the line that's kind of only on a point because instant rate of change means 1 point, exact point in time. So I'm just gonna draw a slope or a line that kind of, let me not use that. That kind of like is close to the behavior of the actual curve, if that makes sense. So I'm gonna draw this line going through this point, and it's kind of like, it's behavior near the point. The line's behavior is very similar to the function's behavior near the point. That's how I'm drawing these lines. So now I'm gonna draw another line on B, like so. It's my best. This part is not really touching the line, but it's the best I could do. And then another line up here, and another. So this is how we're going to figure out which of these points gives us the highest or the fastest speed, aka steepest slope. So let's just pull this down. So this one's A, B, C, D. So we look at this, right? What would you say is the steepest? This is for everybody. Let me just label this. So this was point A. This is point B, point C, point D. And again, in this particular class period, they were divided between A and B. But go ahead and try to look at this visual. Which one, which point or which line looks like it has a steeper slope? Or the slope is, or the line is very inclined upward is what you want to think of this as. I know there's something in the chat there. I was just letting somebody in here. Let's see what we got. So we have a guess here, B question mark. Does anyone agree, disagree?
I'll say B.
Okay, we also got another agreement for B. Looks pretty like the steepest right here. The line is inclining really like upward. It looks very steep. I mean, I agree, it looks steep. Maybe that's why this classroom was basically divided into either A or B. And then, as you can see, C and D like really kind of start to flatten out. Okay, so I agree with y'all. I think B as well. Yeah, I definitely can see that it was hard. Like it's like what like A and B, but I could see that B looks like more angled upward. So I would also agree that point B, the ant speed was the fastest. Its instantaneous speed was really quick. So it's like basically like the ant started to speed up around point A, but then really sped up here and then started to slow down. It's kind of like what I imagine the ant was doing. Awesome. So we're going to apply this idea that the steeper the slope, the faster the speed to figure out where the teacher's going the fastest and what was their fastest speed. So I'm just going to write down that note. So we're going to do steeper the slope, the faster the speed. And this isn't a big idea. It's just a concept we're going to apply. That's just an important thing to know to help us answer this question. So that's why that's there. Okay, great, let's do this. So there is a tool that I provided on Desmo slide 8, and then everyone can access this if you go to the Desmos and go there, but I'm gonna go ahead and just make sure you all have the tool so that you can play around with it too. It definitely would be hard to do this without a tool unless you do eyeball your function, but I definitely recommend using the tool. Y'all can see what different people said here. Maybe we could borrow or take a look at some of their thinking and kind of consider that. So let's see these persons. So it looks like, again, remember we got to choose 2 points in order to find speed. You're always going to have 2 points and you got to calculate the slope between them. So I noticed that's what this group did down here. They used the slope formula and they got 87 miles per hour. So sorry. According to this calculation, like for example, if this was true, that the teachers were going 87 miles per hour, they would for surely at some point in their drive be speeding. I don't know. We don't know if this calculation is accurate. Let's see up here. It says the car was the fastest between the points 2 and 4. And it says when they were at 3, I would say the slope began to get really steep. So notice how they're applying the steepness of slopes here again. And that's what we're going to be doing. And they got a point. We're going to see what we get in a second. And they applied, wow. So they're talking about how they applied the equation from the big idea number 5. They also multiplied by 60. So that's something we can't forget. And they got 72 though. So according to this calculation though, that this group did, they can't prove that the teachers were speeding because they're still below 75 miles per hour. So then let's figure this out. So who's right? I don't know, but I believe both of those students were on the right track, definitely, or on track, you know. Okay, y'all. So what is this tool? This tool basically is the red, right, is our function, the one that the teachers were driving. That's our function. Awesome. But what is this purple line? It's an amazing purple line because this purple line actually is helping us visually see the slopes of the teacher's graph. Isn't this awesome? And we're going to be using this line to identify where were the teachers traveling the fastest. Once we've identified that, we could zone in on some points and we could apply big idea number 7. So say you could play around with it, you can move this. Of course, you don't want to go above 9 minutes because remember that's when the teachers stopped their drive. So we can't go past 9 minutes. So you just want to play around between 0 and 9 minutes and figure out where does the slope look the steepest. And from there, once we've identified where it looked the steepest, we can try to calculate the speed at that location and check whether or not they were indeed speeding. I don't know if y'all see that. It says my connection's unstable. But anyways, go ahead and play around with this, y'all. So again, I put the calculator in the chat. I want to see what you all think. At what point is it the steepest? And for example, once you find a point, right? Let's say just pretend this is totally not the point because look how not steep this line is. But if once you choose a point, right, you just click on the purple dot and it gives you a point. So go ahead and try this out and try to let me know what y'all think. At which point does this look the steepest? Just tell me a point and we can check it out together. Try this out. Hey, y'all, just checking in. So I was just pausing to see what y'all are getting. So again, you want to play around with this tool and you want to tell me at what point the slope looks the steepest. Or as I'm moving this tool on my screen, go ahead and let me know when to stop. Like, hey, that looks pretty steep. Stop there. Let's calculate the speed there. So that's what we need right now. But I want you all to do the thinking because I can't just give the answer. I want you all to apply this. So where does the slope look the steepest? Okay, we got at around 3.18. And this is a direct message that we got. Let me know if anyone else agrees, disagrees. So let me go down to 3.18. Here we go. Yeah, that looks pretty steep. Look at the line, everyone. I like that, right? Once I start moving this up, it appears that it gets like more horizontal and less steep. And before that, it was like kind of approaching the steepness. So I think this is a good point. This is great. I love it. So what this point is, right? We've identified a point that the slope is a steep. And what this point is, and when we're relating this back to our big ideas packet, this point is that term point of interest. It's right here. So remember what it says again. We can estimate and approximate what is the instantaneous rate of change or the instant speed by choosing by choosing points that are infinitely close. So a point that has to be infinitely close to my point of interest. Well, we found the point of interest. Now we just need to choose a second point that's infinitely close to it. Or how you can think of it is just choose a second point that's really, really, really close to this point of interest. Once we do that, once we have 2 points, y'all, we could just find the slope between those two, and that will give us a speed that's going to represent the instant rate of change, or AKA the exact speed that we're going at that point in time. So I'm going to go back here. Cool. So we have our point of interest. Let's work on choosing a second point that's really close to this. And then again, I'll need y'all's help to tell me what's a good point to choose, because you could choose any points. So I'm just going to zoom in around this location to kind of just best help me. And zooming in. Why do I zoom in is because I could start to kind of choose points that are really close to this point of interest. So I could choose points that are behind it, or I could choose points that are before it. Either way, someone in the chat, go ahead and let me know which point should we use. I'll try to pause, and I mean, closer the better. I don't know, infinitely close can look like. So there's and if you're on this with me, just let me know which one works. There's a bunch of different points that are really close to this point of interest, and that's the goal here. We're just trying to find a second point that's really, really close. That is us applying big idea number 7. Again, let me know when I could stop here, or at one point you think we could choose that's pretty close to this point of interest, and we could apply that big idea. Let me know what y'all think. So let's see if any voices that we haven't heard from. What's a point, just any point I could choose that's close to this? You could choose so many different ones. These are all very close to this point. What would be a nice point?
4.97.
4.97. So like up here, when you're saying 4.97.
Yeah.
So like we'll zoom out a bit, and we have to find 4. Somewhere up here. Okay, so you're saying let's choose our second point to be this one?
Yeah.
I mean, that's it. Thank you for participating there. Awesome. So would you say that these 2 points, or would you say that this second point right here is very close to that purple point? Or is it kind of far away?
Wait, never mind.
So would you say far away or close? I couldn't hear that last part. So we're here. We have this idea that we could use this point. And then for me, I just asked a clarifying question like, so is this point, the second point right here, really close to the purple point? In order for us to use big idea number 7, we have to choose a point that's really close to the point of interest. If you disagree or agree, cool, but how can we kind of choose a closer? Can we make this closer? Can we move closer to that purple point?
Yes.
Okay, we got a yes. Okay, so we can move closer. So these are all points that are getting closer and closer. And if we want to get even more closer, you could zoom in. And you could choose really close points to this purple point. So that's the goal. So big idea number 7, you got to choose a point that's really close to it. I love that you brought in that 4 point something. I mean, like if you think of it, 4.1 something and 3.18, they're about a minute apart. But I would say that if you're driving a car, a lot could even happen between minutes. So that's why we want to choose, get even closer. So we could find out what's happening exactly at this point in time at around 3.18 minutes, what's happening there. So that's why we want to choose a point that's really, really close. And these, take a look. They're close because look at the X values. So for example, 3.18 and then 3.19. They're very close, but we could even get even closer. So to this group, just let me know which one to choose. Any of these could work actually. Um, I just want to settle on something that you all agree on.
3.19.
3.19. Let's do it. Yay. Thank you so much. 3.19. Oh, that's over here. Let's do it. There we go. So maybe if someone can type that, I'm gonna forget this point. Let's do it. I believe these 2 points are really close. You could go even closer though if you get a better estimate, but let's stick with this one. So 3.19 comma 1.6337. If someone could put that in the chat for us, because then once I let go, I'm really, really bad at memorizing numbers. I can get the 3.19, but that second one, I mean, if I tried, maybe, but if we could just write that in the chat for us. Yay, I see something in the chat. I hope it's this point. So I'm gonna let go. That's why thank you so much, Sincere. That's why, like in your groups, when someone's like doing something on Desmos, it does help to have another person either writing or verbally kind of saying what to do next. Awesome. I'm just gonna go ahead and just write this point right here in this tool, just so we don't forget it. It wasn't it 1.6337? Let me see. Yeah. So there's just a little decimal missing there, but I figured it. Yay. Okay, so we got 2 points. We got a point, right? First off, we've identified that purple point because the slope was really steep there. Now, because we needed to apply big idea number 7 to find the instant rate of change or the instant speed, right? We needed to choose a point that was infinitely close to that point of interest. And that's what we just did. We found a point. They're very close together. Awesome. Now all we got to do is find the slope between the 2 points. And then we're going to be pretty much there. Except don't forget to multiply by 60 because remember, we're still in minutes per mile and we want to convert to miles per hour. Let's do this, everyone. Let's find the slope now. That's the next thing. Again, notice how I'm just keep going back to big ideas because all their stuff is there. And you also want to make sure you reference it, when you're doing your stuff. So let's do it. So I'm going to call this one X1, Y1. So now I'm going to find slope. And then we got X2, Y2. And then I'm going to go ahead and find the slope of this. Again, as a reminder, our formula is, write it down here, it's Y2 minus Y1 all over X2 minus X1. We hit equal. So Y2 is going to be 1.6337 minus, and my Y1 is right here, 1.6207, all divided by, crooked division sign, I know, all divided by, and we have to do X2 minus X1. So 3.19 minus 3.18. So now we got to just, use a calculator and start to calculate this. So I'm going to use my phone. So I'm just going to do it like separately, top and bottom. Again, make sure that you're either writing this down on the piece of paper and you're fully understanding like what we're doing and why, because that's the most important thing. You don't just want to be blindly following along. Make sure that you're understanding, because then otherwise, it won't make any sense. You'll be wasting your time. So I got 0.013 for the top. For the bottom, I got 0.01. And then remember, guys, that this is miles per minute. Cool. And I'm going to go ahead and wait. I'd like you all to tell me what you get when you do 0.013 divided by 0.01. And then I'll wait until we get an answer there into the chat so that we can see what we get. And we're gonna, like, I feel like once we get this answer, we'll be able to determine whether or not the teachers were speeding at any point, because we've identified first off a portion where they were traveling the fastest. And if at that portion, when they were traveling the fastest, they were speeding, then great, we proved that they actually earned the ticket. But if they weren't speeding, then we could prove to the, we can decide that they're not guilty because we're the traffic court judge actually.
Isn't it 1.3 like the chat says?
Okay, you got it too? Yay. Okay, so 3 of you got 1.3. Awesome. In agreement there. Great. So we got 1.3 and it's going to be miles per minute. Miles per minute. All right, y'all. So remember, we got to convert this to miles per hour. Do you remember what we can do here? What do we multiply by?
60.
Yes, we multiply by 60. And because I'm out of space, usually I show the cancellation, right? So 60 minutes in an hour, but the minutes will cancel out and you're left over with miles per hour. It's just I'm out of space. So let me just make this equal. All right, so all we got to do is 1.3 times 60, and we're going to get miles per hour. Again, remember, minutes cancel out. I just ran out of space. And let me know what y'all get once you do this calculation. All right. Thank you so much, Tori. I got the same thing. When I multiplied by 60, I got 70 miles per hour mph. Oh, I'm sorry, 78, LOL. I got the same thing. I don't know, I swear. It's on my phone right here, so I don't know why. I just had a little brain fart. Yes, 78 miles per hour is what I got. So we've identified a point in time when the teachers were traveling the fastest. We did this because we saw the slope was the steepest there. Then we calculated what was the instant speed at that point in time at around 3.18 minutes. We calculated that they were going about 78 miles per hour at around 3.18 minutes. So 3 minutes, 18 seconds, I guess. We think of it like that. So then would we say that the teachers then therefore are guilty of speeding at some point in their drive? Let's see what you all think. So what do y'all think? So were the teachers at any point in their drive guilty of speeding? And this is open to anyone here. Okay, we got a yes there in the chat. We got a yes. What does everyone else think? All right, we got another yes from Jasmine. How about Jalen, Sincere, Simia? What do y'all think?
Yeah, I think yeah.
All right, yeah, we've identified a spot where they were indeed going above 75 miles per hour. Remember, you showing your work, make sure you do, and you make sure we understand what we just did here and what big ideas. You can totally take a screenshot of this as well, but make sure that you are justifying and elaborating what we just did. That's the key part. So let me just go back to our summative. So what we just did, we applied steeper the slope, faster the speed. We identified that at the steepest point was at x equals, or t equals, whatever, 3.18 minutes. So first we identified that that point, that line was the steepest. And then we chose a second point that was really close to that was really close to our point of interest. And again, that's us trying to apply big idea number 7. So these are just little notes for y'all as you're explaining your work to just make sure you include, because this was our process. Again, we looked at big ideas packet. Then we kind of had to talk about the steepness of slopes. And then we identified where a location where the graph where the slope was the steepest. And from there, to apply big idea number 7, we needed to choose a second point that was really close to that first point. And we got 78 miles per hour. So in reality, y'all, you could already be ready to answer number 4. That's why I just asked y'all, do you think they're guilty of speeding? All of you said yes, but now go ahead and make sure you answer the follow-up questions though, right? So you're gonna put yes because, then you're gonna explain it in your own words, your own understandings. So basically what the last thing we'd have to do is just try to figure the answer or figure out how to start, because we're at 11:19, how to start number 3. By the way, I did finish talking about number 3 yesterday. So yesterday I did hold a group. So you could also look at that video if you still want to look at how to do number 3, but we could go ahead and start it. And then yes, and then thank you, Jasmine. You said yes because it passed more than 75 miles per hour. Awesome. And you could even say because we use instant rate of change and so forth. Or you can consider what we say for number 3. Yay, yes. Okay, let me go ahead and clear my screen. Let's quickly, in this last few minutes that we have, let's see what did Miss C do. So if y'all remember the context of the problem, Miss C was she's a math teacher. She knew the speedometer was broken. But what Miss C was doing, if we look back up at the problem, when she was trying to argue to you as a traffic court judge, she was trying to say they were not speeding. She says this, let's remind ourselves, the speedometer was broken, cool, but she was taking calculations or AKA reading the odometer every minute. So Mrs. C was able to read or calculate the average rate every minute. So after every minute. So what that means is that she wasn't able to calculate between minutes, if that makes sense. Like she's not able to calculate like 2.5 and 3, or she's not able to do what we did. She's not able to do what we did right here in number 2. We had to choose 2 points that were infinitely close to each other. Miss C kind of has a disadvantage. She was only able to calculate points that are apart from each other by a minute. So that's what Miss C was doing. Because physically, as a human, it'd be hard to do more calculations than that, especially when you're driving. So that's what Mrs. C did. So now we're going to see what was the fastest speed that Miss C could have possibly measured for the car if she applied her method correctly. So it's not like Mrs. C is lying. It just could be that her method is not going to give her the correct fastest speed. So it's not that she's lying, but she did something, and we got to kind of replicate what she did. So let's go ahead and zoom on out. Just going to zoom out. So these were the points we chose before. Zoom out. Let me get rid of that because we're done with that. Okay, so let's say Miss C knew for sure that they were going the fastest between 2 and 4 minutes. Why she would know that is because between 2 and 4 minutes, the line kind of shoots upward. The graph shoots upward, right? So it looks the steepest there. And because Miss C can only measure minutes that are apart, what are like 2 possible points she could choose? And this is open to everyone so we could get some ideas out there. Let me also get rid of this purple thing. We're not using this particularly right here. There we go. It's gone now. So let's say Miss C knew that between, let's say 2 and 4, she knew that the teachers were probably like speeding up a bit in the car. But because Miss C was only calculating for every minute, what are 2 points that perhaps she could have chosen to calculate what she would think would be the fastest speed. And basically what we're looking for is any 2 points that are a minute apart, because that was Miss C's method. She only could choose points that are a minute apart. What are some 2 points, y'all? Any 2 points that are a minute apart. Let me give you an example. So for example, if you look at the input or the X value right here at 1 minute, right? It's 1 minute. They went a distance of 0.345 miles. Then another minute is at 2 minutes. They went a distance of 0.485 miles. Then your next minute is at 3 minutes. They went a distance of 1.388 miles, so forth. So these are the different points in your graph that are apart by a minute. Just let me know which 2 points we could choose for Miss B. I'm sorry, for Miss C, that she could have possibly used to, you know, to determine whether or not they were speeding or not in her case, because she was only able to do it apart with minutes. Which 2 points? You could say between these 2 minutes, and we could try that out. All right, let's do it. Yes, thank you, Rosario. So let's do between 2 and 3 minutes. I like that you chose that because I feel like Miss C knows that around between 2 and 4 minutes, they were increasing their speed or going faster, right? So why not choose some area between there? So let's say 2 and 3 minutes. So at 2, it's 0.485. At 2, 0.485. That's 1 point. And we said second point would be apart by a minute, right? Because that's Miss C's method. It's going to be 3 comma, please be a nice number, 3 comma 1.388. Okay, I mean, nice enough. I was able to memorize it. All right, so let's say Miss C was like arguing like, no, we're not speeding. And let's say that she identified this area between 2 and 3 as the steepest slope. So then when she calculates this, let's see what she gets. Like either she was lying or she really got something different when she did the calculation. So I'm assuming the teacher shouldn't be lying. I just feel like it's just a different thing they did. So once you hit this point, we're at 4 minutes. Let's see if we could get this done. Let's go ahead and now find the slope between these. Again, whenever you have your 2 points, just find the slope. That's going to get you your speed. So we got, let's make this x1, y1. We got x2, y2. And then we're going to use handy dandy slope formula that I've been writing all the time. Y2 minus y1. That's a y. Yep. All divided by x2 minus x1. All right, so y2 is 1.388. Minus y1 is 0.485. And then divided by, and we're just going to do x2 minus x1, so just 3 minus 2, of course, because it's apart by a minute. Then from there, you all can go ahead and finish up this calculation. Keep in mind that it's in minutes per mile, so don't forget to multiply by 60. We're going to have to conclude this since miles per minute. Oh, that's a mile. Because I got a conference coming up, so that's why. But let me know if anyone has any teeny last minute kind of things before I end this meeting. So again, I'll try my upload this to the soonest that I can. But again, this is unfinished, so you're gonna have to finish at number 3, y'all. Or look at yesterday's video. I sent it and I did finish number 3. Any last minute questions or anything before we head on out? Thank you everybody who is here. Make sure you take pictures or anything to help you out. Okay, awesome. If there's no questions, y'all have a great day. It's been great. Thank you so much. Yay, yeah. Thank you so much for your participation.
Thank you.
Yeah, of course. Thank you. And then even if you weren't participating, you were like visually participating here with us today. Thank you so much for being here. All right, y'all enjoy. See ya.